Okay, I had to redo that. Hopefully everything is doing well. The sound that problems that we're having forcing us to redo these videos. But welcome to the Honest Investigators Talk Shop show. This is for Saturday, a redo of Saturday lecture last 6th of February. I'm Doug Bundy, president of the Larson Research Center, where we are unveiling the universe of motion. Today's actually Thursday, but this is a redo of last Saturday's, the 6th of February 2016 lecture, because it didn't come out very well. The audio came out all garbled. So anyway, in parts 1, 2, and 3, and 4 of this lecture series, this is part 5, we presented a general overview of the work and purpose of the LRC and the major acronyms and so on that we use throughout these lectures. So please refer to those videos for orientation type information and to catch up. They're all available on our YouTube channel as well as on our Google Plus page. Well, they may not all be available on our Google Plus page now because we have changed from our encoder from Hangouts on Air to this new YouTube encoder that we're using, and so they may not appear on our Google Plus page, but they will be all on our lrcphysics.com website. So at any rate, like I said, we have to redo this. So this is lecture 3, part 5 then of that lecture that where the sound got kind of messed up. So we'll try to do this right now. It's entitled A Multidimensional Scalar Number System, and we will try to excuse me, try to make sense of this by revisiting this idea of Larson's cube. Remember, Larson's cube contains all these different dimensions: the 2 to the 0 dimension, the 2 to the 1 dimension, the 2 to the square dimension, and 2 cube dimension. We've talked about that and explained how that is analogous to the binomial expansion of the tectactress. And we covered that in our lecture, previous lecture, so please refer to those to understand that. But the important thing here is that this follows the 2 in cube progression that is so important in understanding the new mathematics. And we had somebody say, well, we need to, it would be much more, it would be easier to understand this lecture, a commenter said, if we went from the mathematics to the actual physical entities such as photons and fermions and so on. So bosons and fermions are the standard model. So we're going to try to do that. We'll have to gloss over some of the details, but those are available in previous lectures, like I said. So in starting off, the important thing to understand is this 2 in cube progression. If it starts, of course, when n is 1, it goes 2 times 1 is 2, cubed is 8, and then it goes to 64, because 2 times 2n is 4, and 4 cubed is 64, and then 8 cubed, or 6 cubed, 2 times 3 is 6, and that cubed is 216, and then as shown here, the next one, we don't really show it, but we put the It's too hard. We ran out of room here, and it's too difficult to construct this, but it would be 2 times 4 is 8 cubed, which is equal to 512. But as we've explained, we can go and represent this unit 1 as a square root of 1, and there's a reason for doing that. But so in this next line down here, if we do that, we see that the same equation is equal to the square root of 64, which of course is 8, and the square root of 4096, which is 64, and so on. So we're expressing it in square roots, and you'd wonder why we would do that, but that's because, as we've explained before, there are actually 3 units that can be used to describe this 2n cubed progression. One is the square root of 2, and the other is the square root of 3. So when we change the n equal to the square root of 1 to n equal to the square root of 2, we get these red equations, the same progression, but now expressed in terms of the square root of 2. And also then we do the same thing for the square root of 3. When we make n equal to the square root of 3, we get these numbers. And the reason that's important is because it enables us then to use these square roots as in the formula for area and volume that are continuous values that correspond to physical expansions and physical equivalents, we might say, of these mathematical numbers, because remember that nature doesn't expand in squares and cubes, but rather in circles and spheres or balls, in volumes like that. So that's important, and it's very interesting, and you'd have to go back to our previous lectures to see what this is all about, because we're not saying that they are equal to the numbers in these cubes, of these stacks of cubes, but rather that they correspond. So if you've got a stack of 216 one-unit cubes, there is a definite two-dimensional area and two-dimensional volume, and one-dimensional area and one-dimensional volume, and three-dimensional area and three-dimensional volume that correspond uniquely to that stack. So that's very important, because then it enables us to do what we might say an index there. All right, so what turns out then, if we start at the beginning to try to explain these things, it's essentially, as the Bible says, let there be light. So what we're really saying is let there be this eternal three-dimensional progression, and then let there be an eternal 3D oscillation in one aspect or the other of that progression, and then just follow the consequences as they develop. So that's what we will do to try to explain this. And we've seen this chart before. It's a very important chart that shows that an eternal 3D scalar progression of space and time, what we might call the natural or eternal progression, really sets the stage for everything that follows. We can see that as space progresses for every unit of time, we would get, if we say that space is plotted here along the horizontal axis, and this time progression along the vertical axis, and these are units, and we can see that in 2 units of time and 2 units of space, we would be at this point, and then in 4 units of space or time and 4 units of space, we'd be here, and so on. It goes by twos then, so 2 over 2, 4 over 2, and 6 over 6, and so on. And that's a one-for-one progression. In other words, 1 unit of space for 1 unit of time gives us what we would call the unit progression, or you can, if you want, call it a unit speed. And we would identify that with the speed of light But this is not light. This is the universal progression of space and time, but we'll see how light comes out of it. And that happens as we introduce oscillations into one aspect or the other. Now, if it's a space aspect that oscillates, and you have to understand that this is a 2D slice of a three-dimensional representation, because it's so difficult to do it in three-dimensional figures. We're just doing it in 2 dimensions, but with the understanding that we're representing 3 dimensions. So we've got an expansion in 3 dimensions of space and 3 dimensions of time. And that is, according to the reciprocal system, what we have, that time and space are really just reciprocals of one another, and the properties of one are the properties of the other. So as space, let's say, progresses, but at some point, like represented here, it suddenly decreases, and so instead of expanding as a ball to the next unit of volume, it actually collapses to 0 volume. Then the result, because time continues to increase normally, the result would be this diagonal, which we're saying represents a 3-dimensional XYZ change of 1 unit. So that would be, the length of this would be the square root of 3. So the constant 4/3 pi times square root of 3 would give us the volume, and that decreases as this arrow goes to 0. And then as it increases in the next half of the cycle, then it goes to full volume, and then 0 volume, full volume, 0 volume, full volume, like that. And we've shown that in more detail again in previous lectures. But as a result, then this goes nowhere. It oscillates over 1 unit. And the same thing with time. If the time expansion suddenly reverse direction and collapsed to 0, and then expanded over the same unit, while space progresses normally from unit to unit, then we would get that expansion, contraction, expansion, contraction cycle in time. And then that gives us these 2n cubed progressions that we can combine into one. But the space-time equation of that is, if it's in time, is equal to 2 units over 1, because it's time here in the denominator that is oscillating over this 1 unit. And same way with space. And we represent the space aspect in red and the time aspect in blue. But this is the inverse, you see, because they're orthogonal here. Then one is the inverse of the other. It's actually on the opposite side of unity here. So this is in red, but the space-time equation now, because it's space that is in the numerator, it is oscillating. So we have 1 in the numerator, while time is progressing normally. So now this is the ratio of space to time when that happens. And we see here that would be then 1 over 2, and then the next cycle would be 2 over 4, and then the next one 3 over 6, ad infinitum to n over 2n, which is just the reciprocal of this one, which would start at 2 over 1, 4 over 2, 6 over 3, ad infinitum to 2n over n. Now, that should make sense by now if you've been following these lectures. It turns out then that what we have are these 2 oscillations. Now, I wasn't able to make them exactly how I wanted because I don't have the facility with the graphics that I need. But at any rate, here, if you can imagine this one over here is red and this one over here is blue, then what we have is this oscillation, continuous oscillation in space, produces this 1/2 ratio of space and time. Whereas in this one, if that's blue, then you'd see that this is time that's oscillating in this fashion, giving us just the reciprocal of 1/2 or 2/1. So that's the same thing that we've just looked at here, but put in a different fashion. Here, where there's no oscillation, we have unit progression. So if space oscillates in this fashion, then it produces this less than unit speed, if you will, 1/2 ratio. And if time, on the other hand, oscillates, it gives us this 2/1 space to time ratio. So now if we look at this, we can see that these would combine, because the space or the time oscillation would cause the progression to proceed in this fashion. And I think I've got that. Darn, I thought that would be that should be 2/1 there, or not even there, but because I didn't represent it for the space unit displacement ratio. But here the time oscillation causes what we call the time unit displacement ratio, and then the vertical progression would be the space unit displacement ratio. So this red line is where the space is oscillating, and this blue line is where the time is oscillating. And we could just ignore, in fact, let me for just a minute here, if I can, let me pull up my marker system. I forgot to do that. Okay, there it is. All right, so we would cross this out here. I don't know why that is on there. It shouldn't be so. But so here in the tutor part of it, when we combine them here, remember we had space over time. When the space is oscillating, gives us this ratio of space and time. And then when time is oscillating, it gives us this ratio here, 2/1. Now we call this one because it's represented as progressing horizontally, we call it the tutor, the time unit displacement ratio. And this one would be the space unit displacement ratio, which is the reciprocal of that, as we've just explained. And so because they are orthogonal and progressing one horizontally and the other vertical, there's a possibility that they could collide. If they do, then we get this, which we represent as an ST unit, which is a space unit displacement ratio combined with a time unit displacement ratio. And we use the pipe sign here to indicate that combination. So this S, capital S, represents this ratio, and this T, capital T here, represents this ratio. So when we combine them together, then we can use the scalar mathematics, which is a little different because we're treating these ratios as whole ratios, not as numerators and denominators. So when we add them or multiply them, we operate both on the numerator and the denominator. So in this case, we add them up and we get 1 here, and then 1 in this middle term, which I'll explain in a minute, and 2 in this term of the tutor, the T, and that gives us a 4 in the numerator, excuse me. And then the same thing with the denominator, 2 and 1 is 3 and 1 is 4. So we have the total motion in this combination, in this ST unit, of 4 units of motion. And if you go back to our previous slide, you could see how that these two, denominator and numerator, because this is an oscillation involved, always would come out the same when they're combined equally like this, or whether they're combined unequally, because even though this number is less in both cases, when the oscillation causes a change in the unit ratio, we count for the other part of the oscillation in this middle term. In other words, here you can see this 1 could be the, let's say, the outward motion of the space unit when it's expanding, and then this 1 in this term here represents the inward. So you've got 2 over 2 really, but we've split them up because of the different directions. In the same way in the denominator, here you've got 1 that's outward, and we put the inward cycle over here. So you can see that if they were unit expansions and there was no oscillation involved, then this term would be 0 over 0, and this would be 2, and this would be 2. So 2 plus 0 plus 2 would be 4, and 2 plus 0 plus 2 would be 4 as well. But the oscillation requires us then to change the equation to this. Now, I hope that makes sense. Now, so what that would represent there is this term here. You can see where the, and that is wrong, darn it. It should be capital S pipe capital T, and it's not. It's S diagonal slash T, which is misleading. But anyway, it is 4 over 4, meaning we've combined in their most simple form, simplified form, these two equations, giving us this path here of a combined, it's kind of hard to do with a mouse to draw a straight line, but that is the path of this equation here, where the two, the S and the T, combine. All right. Now, remember, this is not necessarily a motion of that we normally think of, an increase or a change from one location to another location, but rather it's showing the increase of size. All right. So that means scalar motion, which is not the same as vector motion, where something goes from one unit to the next, or one location to the next location. This is a different kind of motion that we call scalar motion, a change in size or change in scale. Now, the possibility is, though, that there are other S units out here and other T units out here. So as the S pipe T progresses, then it could collide with another S unit, which would then again change our equation, and the increase would be less than unity, as shown here, or it could combine with another T unit, and therefore its progression would be more than unity. So this is less than unity and more than unity, and here I've shown an example of that. Again, this should probably be S pipe T uppercase, but here we have the normal 1 over 2 plus 1 over 2. In other words, 2 of the space oscillations here combined together, which gives us then 4 over 2. All right, and that would, as we explained previously with our teeter-totter example, that would tilt our progression to the higher end of the scale, higher than unity. So now we have 6 over 6 units, but that's because the high side is now 4 over 2 because we had, okay, I see, I'm probably not explaining this right. Normally we have 1 over 2 gosh, how do I make these mistakes all the time? This would be the tutor coming in, so it and adding to the other, so it should actually be 2 over 1, not 1 over 2. So you add that then to this normal 2 over 1, and that gives you 4 over 2, so it imbalances this ST unit that is normally balanced like this. You're adding another 2 over 1 here, and that then gives you a total of 6 over 6, but it's unbalanced to the high side. All right, now this one I think is correct because it's showing that we take a balanced ST unit that has a 2 over 1 space-time ratio on the red side and a 2 over 1 on the, no, that's wrong too. I think I don't understand what I was trying to say with the equation here. I'd have to revisit it. It might have been too long. But the point is that the T unit coming in would unbalance the ST unit to the high side, and S unit joining an balanced ST unit would unbalance it to the low side. And we've explained that with our teeter-totter examples in the earlier version of our earlier previous presentations, so you can see that. I was trying to explain something here and I don't now recall exactly what it was, but that's what it should be. Okay, so we can look at the same thing graphically here. This is what we're trying to show. We can add more than one unit to either side. So if we added, if we take the, and this is, here's another thing that's wrong, and I missed that. I've corrected it in other places, but this would be wrong if there's no paren here. So we need to add parens here so that this would be whatever n is, whether it's the square root of 1, the square root of 2, or the square root of 3, there's two directions that goes in, and so you multiply that times 2 or whatever. Actually, this is the number of the progression. So if we're talking about this case here where we have 2 units we're showing, then that number would be 2 of the units, whatever these units are. And of course they're in 2 directions, so we multiply it by those 2 directions. So 2 times, let's just say it's n is 1 in this case, or the square root of 1. 2 times the square root of 1 is 2, times 2 is 4, and then that cubed would be 4 cubed, or 64. And that's exactly what we have in our progression. Our first progression is 8 units, a 2 by 2 by 2 stack of 8 1-unit cubes, and then the next one is 64 1-unit cubes. Well, you see, that's the exact same thing here. Only what we're showing is that now the reversal doesn't reverse it every unit, but has to go actually out to 2 units, and then it reverses and comes back 2 units and so forth for 2 units as I try to draw this with the mouse. And that gives us then a different progression. In other words, when these things combine, it changes the n here. Not the n there, but the number of n's that are involved. So this would be 2 n's. We can go clear on up to infinity, I mean, in theory. And the same thing on the time side. We can go if there are 2 units added, then that's the same as this progression here, 2 times whatever the n is, square root of 1 or 2 or 3. And so graphically, then that oscillation would go over 2 units like that. And of course, it's the time and space are not going to change, so the frequency would be changing here. All right, so what we're saying then is that at unity, where there's no oscillation, we've got 1 unit of space for 1 unit of time. That's our equation, and we call that, and we're coloring it green, and that would be our c speed when we get into the physics. And it comes, though, from the equation of Pythagoras, where n is equal to 1 square plus 1 square plus 1 square, because this, again, is a 2-dimensional representation of a 3-dimensional graph. And so we got 1 in the x-axis, 1 in the y-axis, and 1 in the z-axis. And adding those together, it gives us the square root of 3. So here I'm saying x and y dimension are shown, but z dimension cannot easily be shown because it's into and out of the page. So with that understanding, though, n is dependent upon what we're looking for, because there are 1-dimensional, 2-dimensional, and 3-dimensional elements in each one of these oscillating cubes, stack of cubes, if you will. So when this happens, this is greater than the unit value of c in the blue, and then of course this is less than the unit value of c in the red. The st, the space over time equation for this particular combination would be 2 units of space for every 4 units of time, which is less than c. But over here it's a reciprocal. It would be 4 units of time, of space, 4 units of space for every 2 units of time. So you see how that works. Now we can do the same thing. In order to show all this, though, that's the background, but to show this in some efficient manner, we use this schematic of red, green, and blue, where the red is this lower than c speed, and the blue in the schematic is higher than the c speed, the unit speed, and green is the unit speed. So in this schematic representation of this equation here, which is balanced, one space oscillation combined with one time oscillation, we see that that would be equal or balanced. So the middle color here is green, and that's our 4 pipe 4 total units of motion involved. And that's our basic S pipe T unit that we are talking about, that proceeds at or progresses at unit speed, okay, because we've got this combination here that is progressing in the vertical dimension. I don't like to use dimension, but the vertical direction, and this in the horizontal direction. When they combine, then their combined is in the diagonal, and that's represented by the green. Okay, but if we now unbalance that and add one more of these to the red side, then we change the center color to red, indicating that it's unbalanced to the lower side. And this is the equation giving us 6 pipe 6 total motion. And then just the opposite on this side. If we have the balanced unit and we add another t to that side, then we have the 4/2, which is unbalanced to the high side. And so the center color of the schematic representation of this motion, which is 6 pipe 6 motion, the same as the one that's balanced in the opposite, unbalanced in the opposite direction, then we color that blue, showing that the unbalance is to the high side. And this is the equation that goes with that. So that should be real simple to understand. Now we can combine these so that if we have that one that's unbalanced, you see here, to the low side, and we add one that's balanced, 1/2 and 2 over 1 is balanced, then that gives us the same 6 over 6, which you see, if you add those up, you can see what they come to. 3 over 6 plus 3 over 2 plus 4 over 2, which now is the same as 10 pipe 10. In other words, 4 pipe 4 plus 6 pipe 6 is equal to 10 pipe 10 as far as total motion is concerned. But the balance is quite different. It's unbalanced to the lower side. So the schematic is to show that is colored red. And if we put the actual equation in, we see that there is quite a bit difference in the equation. We can see the imbalance in the equation. Here we just get a notion of it, but here we get the actual imbalance that's involved. All right, so now if we go to we can do the same in the opposite direction. Again, in a balanced unit, this is a ST unit that's coming along just fine, and it collides with an unbalanced unit that's unbalanced to the high side. All right, then it unbalances it even further, and we get the same schematic, and we get the same pipe result. 4 pipe 4 plus 6 pipe 6 is still equal to 10 pipe 10 as far as total motion is concerned, but we see we've got the reciprocal result, so that the 6 over 3 is now on this side, and the 3 is in the denominator and the 2 is in the numerator, as far as the equation, which is just the opposite or the reciprocal of the one before. So you see, we're showing the results in two reciprocal fashions. All right, so as a result of those combinations, possible combinations, we can then determine, and you know, they can go higher, but we're only dealing with the first possibilities. We don't want to get into the unstable possibilities, because in the standard model there are 3 families, and this would represent the first family, which is stable. But besides electrons, we have mesons, and then there's another family where they're unstable, but the combinations really follow the same pattern. But this is what we get. So if we combine 3, and we'll talk about why we do 3 to begin with. We'll talk about why we do 3 beginning. Let me back up. We'll talk about why we choose to do it 3 initially, then use the number 3 initially in a minute. But these would be boson combinations, because they are stacked in a way that you could stack as many as you want and there would be no problem. Just like stacking parallel sticks together. It doesn't matter. It would be easy to add another one or 3 more or 4 more, because they are stacked parallel like this. It makes it easy. And that's the nature of bosons. This would be our W and Z bosons of the standard model, and the W and the plus W and the minus W, and then the Z is a little more problematic, but it's a combination of these two. It doesn't live very long, but we can talk about how that is involved in beta decay of hydrogen and at some other point down the road. But the point is that bosons, when you combine 3 of them, combine very easily like this. But fermions have a different configuration, shown here as a triangle. That doesn't necessarily mean that, of course, that they're formed in triangles like this. It's not to be taken literally. This is a symbol, but it's to show the various possible combinations as fermion combinations. You can have 3 that are balanced units, 3 ST units that are balanced, these 3 here, but they are configured in a triangle, showing that there's a different physical configuration between the two. But because they're all 3, that would be the neutrino and antineutrino. And then we could add 1 unbalanced to the high side, and that would give us what is identified as the anti-down fermion or quark. These are called quarks. And then we could add 2 of those, which would give us the up quark. And finally, we could have all 3 of them be unbalanced to the high side, and that would give us the positron. In the same way here, starting with a neutrino, we could add a low side unit, ST unit, shown as the red here, and then 2 of those, and then 3 of those would give us the electron as shown. So we end up with a down quark, an anti-up quark, and an electron in this fashion. And then over here is the mirror image of those. This is called chirality, and we would explain that probably further on. But the idea then, it should be clear how we go from these units of motion to actual physical entities such as photons and fermions. Now, if we go back to our mathematics, we can see how useful this is. We can change the unit from 1. Well, it's actually not changing in this case. We're changing the square root of 1, which is 1. So it doesn't change much. But we can do the same kind of mathematics that we do when we use n equal to 1. And we can change n equal to square root of 1, or we can change it to the square root of 2, or we can change n to the square root of 3, and that all applies to the same ST unit, the same combination, because each combination has 1, 2, and 3 unit elements in it. So if we take that balanced unit, the one we start with, where we combine 1 over 2 with 2 over 1, we can look at the one-dimensional aspect of it, or the two-dimensional aspect of it, or the three-dimensional aspect of it. Now, that's important to understand, and we can kind of look at how that how that works in this case, where we change n from square root of 1 to square root of 2, okay, and add it add a balanced unit to an unbalanced unit that's unbalanced to the high side. But now with the unit changed from the square root of 1 to the square root of 2, even though we get the same number of total units motion, you can see that even though these are the same numbers, 4 plus 6 is 10 in both cases, but it's 10 times the square unit of 2 instead of 10 times 1. So we get a different answer. And so that it would give us a two-dimensional aspect there. And then the same thing shown here when we substitute the square root of 3 for the square root of 1. So we add those together. We still get 10, but now it's 10 times the square root of 3 over, or piped with this 10 times the square root of 3, as far as the motion that is contained in the same unit that we saw before. So now we can go to the electron and see how this works. In the electron, we see that we have 3 unbalanced units. So 3 times the 1 unit unbalance, we've got, it's unbalanced to the low side, so we've got 2 of the 1 over 2 ratios, which would give us 2 over 4, and 2 over 1, and another 2 over 1. That's the equation of this unit here that is shown 3 times in the electron. So we multiply that by 3. Same thing, we can do the shortcut here by just multiplying the total units. And if we do, we get 18 over 18 when n is equal to 1. And the actual imbalance is shown as 6 over 12 plus 6 over 3. See these two, half out and half in. And then this one, 6 over 3, because 3 times 2 is 6 and 3 times 1 is 3. So you add those up. 6 plus 6 plus 6 is 18 in the numerator, and 12 plus 3 is 15 plus 3 is 18 in the denominator. But this is how it changes. All right, and notice then that, see, now this has changed where here we had 1, so we could say that this was a minus 1 because it's to the low side, and this would be a minus 1, and this would be a minus 1, so we could add them up and say minus 3. But you can see that's kind of a hand-waving way to do it, but here we see the mathematics actually coming out. So that 3 minus 6 is a minus 3, and that's exactly what we would want to have. And we can do that, you see, whether the unit is a square root of 1, which would give us this equation, or the square root of 2, which would give us this equation, or the square root of 3, which would give us this equation. So we can do the same things now for the others, the up quark and the down quark, and we get there are 2 blues and a green in the up quark, so we multiply this unbalanced to the high side, blue side, by 2, and that gives us, and we can do it the shortcut way, 2 times 6 in both cases is 12 over 12. And then we have this one green one here that's the unbalanced ST unit, and we can add that. We know what that is, 4 pipe 4. And so we can add those two together, and we get for the up quark 16 pipe 16. And so we can express this in the square root of 1. 16 times the square root of 1 would be the square root, it would be 16, and the square root of 16 is, the square root of 256 is 16. And then we could do it with the square root of 2 as well, and we could do it with the square root of 3 as well, for the same unit, because we have 1, 2, and 3-dimensional components in each one. Now for the down quark, it changes a little bit, because now we're unbalanced in the opposite direction, and we only have 1. And remember, the down had 2 green and 1 red, and so the 1 red gives us the 6 pipe 6, and the 2 green times the 2 times the balanced ST unit of 1 over 2 plus 1 over 1 plus 2 over 1, this equation here, schematically represented like this, is then 2 times 4 is 8 pipe 8. And so if we add that to this one, the one red one, then we've got 14 pipe 14. And again, depending on what n is, we get different values for 1, 2, and 3-dimensional components of the same entity. Now, we can combine those into a proton, so that in a proton we have 2 ups and 1 down. And if we multiply the 2 ups, which are 16 pipe 16, then we get 32 pipe 32. And if we do the same thing for the down quark here, which is a total of 14, and add that to the 32 pipe 32, then the result is 46 pipe 46 as total motion. And again, depending on the unit, we get different 1, 2, and 3-dimensional characteristics or magnitudes. So now we can do the same thing for the neutron. The neutron is made up of 2 downs and an up quark. And if we add up those 2 downs, which are 14 pipe 14, altogether we get 28 pipe 28, and it has one up, all right, which is 16 up quark, which is 16 pipe 16. So if we add those 2 downs, 28 to 28, and one up, 16 to 16, then we get a total of slightly different 44 pipe 44. All right, for the neutron. Now we can add those together with an electron, and we get 108. See, 46 and 44, and the 18 from the electron gives us a total of 108 pipe 108. And so we can work those out for the one-dimensional case, the two-dimensional case, and then, of course, the three-dimensional case. So again, giving us 1, 2, and 3-dimensional magnitudes for the first atom, the deuterium atom, that contains both the proton and neutron and electron. So if we do that, then we have to ask ourselves, what now that we see how the mathematics and all these combinations of colors and so on work, what does it mean? Well, we can think of the low end of the progression as a time pump, because time is coming out, you might say, while space is oscillating. And then just the opposite, over on the high side, the time is oscillating, producing space continuously as a continuous stream. So we can think of it as a space pump, and this is a time pump. And then because these capture the inward cycles of those, then this could be going in the opposite direction, and we could maybe call that a suction pump. I'm not sure exactly if I want to continue with that or not, but we're looking for gravitational effects, which are the opposite of scalar expansion effects, and so that may turn out to be what we need, but we don't know yet. Now, if we take the total of these, which you can see if you multiply these by 2, it gives us 6 pipe 6, or one of them would give us 6 pipe 6, and then we multiply them by 2, it gives us 12 pipe 12, and so that would be the total space and time pumped out of these entities. I know that probably doesn't make a lot of sense right now, but it may as we go down the road to these things. So now if we want to look at the electron and proton 1D magnitudes, we can see, so we're going to use the square root of 1 for the electron, and it has a total number of 18, so 18 times 1 is 18. But over here we have 46, and we could add these together, all of these together, and we see that if you do add them together, you get 10 over 20 as far as magnitudes. We're just leaving out the unit number in this case because it's 1. So we have 10 over 20 and 10 over 13 and 26 over 13 as we add all these various components together, the low side, the high side, and the balanced side, or the neutral side. They all come up, all in there, come up to that equation there. And so when we, and then the same thing for the electron, because there's 3 of those, we multiply the equation for that unbalanced unit there, and we get 6 over 12 plus 6 over 3 plus 6 over 3. And so if we then look at the middle term of both of these, this one for the proton and this one here for the neutron, I'm sorry, for the electron, we see that they're inverse, and they're inverse by the same amount. This one, if you have 13 minus 10, that would give us a positive 3. And if you have 3 and subtract 6 from it, that gives you a negative 3. So they balance, just as we see in nature that they do. Electrical charge of the proton is 1, positive 1, and the electrical charge of the electron is a negative 1. So together they then glom together, and the net result is no charge at all. So that that's a form of hydrogen without the neutron, and we find that it's electrically neutral. Now we can do this in a shortcut sort of way, because we can just count these. That's what we did before we developed the mathematical way of doing it, but you can see this is unbalanced by 1 to the low side, and each one of them are. So that would be 3 unbalanced units to the low side. And this over here, you can see has 1, 2, 3, 4. 1, 2, 3, 4. I'm doing it the wrong way here. So obviously this, yeah, that was a mistake before. This is supposed to be blue here. This was a typo, color-o, whatever you'd call it. But that would be blue. So 1, 2, 3, 4 units. We got them down here. 1, 2, 3, 4 unbalanced units, 1 unit to the high side in each case. And then we have the one that's unbalanced to the red side, ignoring the balanced ones. So we got 4 positive and 1 negative. Gives us a square root of 9, which is 3. And then over here we have the 3 reds that are unbalanced, 1 unit to the low side. So we got 3 unbalanced low sides. So that's 1, 2, 3, which is a square root of minus 9. And people will go nuts and say, well, you can't have a square root of a minus number. Well, we can in the way we're doing it, and we'll explain that later. But that's a shortcut way of doing it. Just add the reds and as 1 unit and the blues as 1 unit, and then compare them. But now we can also change the unit from square root of 1 to square root of 2 in each case. And so now these numbers are going to change in terms of the unit. So it'd be 10 times the square unit of 2 over 20 times the square root of 2 plus, and so on, each time being multiplied by the square root of 2. But by putting them in the red color, we can indicate that the unit is the square root of 2 and not the square root of 1. Where the square root of 1 is in black type, we'll put the square root of, when the unit is the square root of 2, we put the type in red, and that indicates that case. And so we don't have to use those huge numbers of the squares that are involved, knowing that we get the same results in terms of the number of units in every term, but the unit itself is the square root of 2. So we can just go ahead and do it like we did with square root of 1, but then in the end use the square root of 2. So if we do, then we find that what we have in the two-dimensional case is the square root of 18, and in the proton, and in the electron we have the square root of minus 18. Again, we can legitimately use this because of the way we're doing it. So mathematicians might have a fit given legacy mathematics that we're showing a square root of minus 18, but it works in our mathematics. So that's a two-dimensional case. And then in the three-dimensional case, we just change the typeface to color blue, and what we find is, and given the same number of ratios, but the unit number changing to square root of 3 gives us then the square root of 27, and this again is another typo, I forgot, but that should be minus, and that would be a minus square root of 27. So again, they cancel out. So the 1, 2, and 3-dimensional magnitudes of the electron and the proton cancel out one another and are neutral in that case. So anyway, that does it. We've gone from the postulated three-dimensional progression of the reciprocal system of theory, where we get a 1/1 progression, and then we introduce these oscillations, three-dimensional oscillations, and we get to the electron and the proton and the photon and so on. So now that hopefully the audio will have come out better on this version of the presentation than the previous version, so I can replace that. And I apologize once again. I knew there were some more errors in the presentation, but I couldn't find them soon enough to make the changes. But now I'll do that as soon as I say goodbye here and try to be more careful in the future. So now this next Saturday will be our next presentation, part 6, where we're going to take these things to the next level. So we hope to see you then. In the meantime, I hope you have a good evening, and I'll say adieu.